Oh, okay. So thanks, Boumediene, for the invitation. I'm excited to speak here in front of everyone. Please feel free to, like I said, stop me whenever you feel like, and if you want me to slow down or speed up. Yeah. So I'm going to be talking about scientific machine learning today, and scientific machine learning is extremely well, it's a buzzword nowadays, as I'm sure many of you know. It's a buzzword on publications. It's a buzzword on proposals. So I'm not immune to this disease. So I'm also going to try and talk about my take on scientific ML and how we try to do things a little differently or similar, depending on where you're coming from, and how specifically in my case we are trying to link it to dynamical systems, which is also the topic of this special interest group. And finally, since I do come from from the U.S. Department of Energy, how we can draw sort of connections between the work that we're doing in terms of algorithm development and method development and applications that are relevant to at least the US taxpayer. So let's move on. So this is in some sense the outline of my talk. There will be some bleeding over between the different bullet points over here. So first I will talk about an introduction and why scientific ML is so important to researchers, both from the perspective of it's just a cool topic to work with, and also the fact that there is a lot of funding, a lot of institutional support for this type of research. And then we look at how we've done research with our own sort of interpretation of SciML and how that fits into the funding priorities of DOE. I do have a topic 5 that's listed over here, but I don't think I will have the time, or I don't think this is the right venue to talk about edge computing. But a lot of the methods that we are developing, we're also developing the entire spectrum of the application of these methods. So not just the math and setting it up and toy problems, but also taking it to like climate codes and fusion codes that have been developed for the last 30 to 40 years. So in some sense, all the methods that we develop today are not meant to replace what already exists, but to complement them. And so time varying, we might have a discussion about these, and I'd be happy to show you some slides on them. But for now, that's not a part of this talk. Okay, so I really like starting off all my talks with a reference to this workshop report. You can just Google it to see what at least the United States establishment thinks about scientific machine learning, right? So there's this workshop report called Basic Research Needs for SciML. And what this report tries to do is tries to set out some guidelines for researchers who are perhaps machine learning researchers, or perhaps physicists or people who work in scientific computing, to come together and make some transformative advances that make ML useful for the for people like us, with the dynamical systems community, the weather modeling community, the plasma physics community, things like that. And so they've actually split up the requirements in scientific ML into two categories. Government documents, right? They like having their nicely arranged bins. So the first one is foundational research, which is something obviously that I'm interested in. So foundational research then will have also has its subcategories. So one of the things that will stand out to you is that they want scientific ML developments to be domain aware. So you want to develop algorithms that are domain aware because you are a domain scientist or you're working with domain scientists. So you want to leverage properties of the physics that you're trying to learn into your ML algorithm itself. So some examples are, if you know that there are some symmetries in your data set, or you know that there is some prior information about your data set. I come from a background in aerospace engineering, so I know that any emulation of a flow field needs to satisfy continuity, which is the conservation of mass. So I need to enforce that somehow into my ML algorithm, or I would be pleased if I could enforce that. So that or some structure. So that's what we call domain aware. The second category is interpretable. So it's very fashionable now to import TensorFlow in your Python script, right, and hook up a massive neural network and get a prediction that beats everything that exists so far. But is that really is that really a viable solution to to your problem? Because you might also want certain guarantees about your output. You might also want to interpret your output. So it's important to for example, have some discussion about certainty quantification, about model selection, so that leads to interpretability in your SciML pipeline. And finally, something that is, in my opinion, the most difficult thing to do, especially if you're working with dynamical systems, is to come up with stable, well-posed, and reliable formulation. So if you have time series data that you're trying to fit using an ML framework, more often than not, you will see that robustness is not a given at all. In fact, it's very much like a lottery with the current methods that are out there. But of course, there is work going on there to introduce robustness into ML methods as well. So this is what the Department of Energy considers as foundational research in scientific machine learning. It also has a vertical which it calls applied research. Now, applied research is more about picking up ML methods that are already there or that are sufficiently mature for a particular task, and then deploying it on intractable problems, right? So for example, let's say that you want to build a surrogate model for an Earth system, for the Earth system, and you know that the Earth system data is unbelievably large, right? It's and it's coming from various sources. So you have data that's coming from satellite observations, from numerical simulations, from sparse measurements on the ground, from sounding balloons. So you have this really very complicated training data set, for lack of a better word. And how do you then use all this to come up with better forecasts for your Earth system, right? Classical methods would be something like 4D VAR data simulation, but what the DOE is looking into is, okay, can we come up with, using well-established machine learning techniques, that can do data fusion more effectively, for example, right? So that's, and especially when it comes to really large data sets, right? So then another example is ML enhanced modeling and simulation. This is something that I did in my PhD, but the idea is, if you're working on fluid flow simulations, occasionally you run into the closure problem, which means that your numerical discretization does not have the resolution to support all the frequency, all the wave numbers in your flow field. In such cases, you need to provide correction models, which historically have been algebraic in nature. But it's possible that you can use data to actually inform these correction models to get better agreement with some quantity of interest. That is your final outcome. And this is basically something that comes in under the applied research category. Of course, there's bleed over between the foundational and applied research verticals, but this is the basic sort of split between the two, right? So the third vertical, so the third subcategory is intelligent automation. So over here, think of optimal experimental design. You want to use some sort of strategy to optimally sample a high dimensional parameter space to generate training data. So there are these meta modeling strategies that you can use to come up with better exploration of your parameter space. ML does help you accelerate that. Okay. And so today we will be talking about domain-aware surrogate models. So in some sense, the research that I will show to you today will have sort of applications, or we can be sort of forced into one of the categories on both these slides. Okay. So in particular, what I will be talking about is domain-aware surrogate models, right? And so you might ask this question: why should we use scientific ML for surrogate modeling? And there's various reasons to at least attempt to do so. Some of them are over here. So a surrogate model by, it's not implicit in the name, but it's implicit in the understanding that the surrogate model is faster than the full order model. So instead of solving a complicated set of equations, you solve you use something that is far faster to evaluate the forward problem. And so you get computational tractability, and that has a lot of downstream effects. For example, you can, as in point 3 over here, if you're doing optimization with your surrogate model, then you get dramatic improvements in time to solution by using these surrogate models, right? And then point 2 over here says that occasionally your best guess of the physics, or your best understanding of the physics, may still not be capturing all the the hidden correlations or the hidden mechanisms that are actually present in your data set. So in some sense, having data driven surrogate models can offset this lack of information. I don't think that's a more particularly strong reason to use surrogate models, but it is one reason, right? I think the increased time to solution, or the reduced time to solution, is a far better motivation for using surrogate models, right? And points 4 and 5 are basically related to point 1, which means that if you are actually if you're doing like an accuracy intensive modeling task, you can in some sense for some part of your forward model solve, you can use a surrogate model. But when it comes to actually obtaining a high fidelity solution, you can switch back and forth between the PD, in this case a PD, or an ODE if it's a system of equations, and the surrogate model adaptively. So think of solving a optimization problem where you're, for example, I'm going to go back to aerospace because I am comfortable with it. Let's say that you want to minimize the drag over a particular airfoil shape, and you know that for each perturbation of the airfoil shape, you have to run a CFD simulation, which is costly, right? You could start off an optimizer by using a surrogate model, which rapidly looks at the shape of an airfoil and predicts what the drag and the lift are, right? But as you're converging in your optimization using a gradient-based optimization, you can then switch to an actual CFD solution to make sure that you're just not relying on a inaccurate surrogate model. So these are some things that over the lifespan of a computational task will amortize the cost. So that's kind of cool, right? Unfortunately, there are some limitations with surrogate models. We are going to try and address a few of these today, right? And these are, I mean, I'm sure you know about them. Some of the limitations are that they don't satisfy constraints that easily. I was giving you the example of conservation of mass. If you build a a map between a airfoil shape to the flow field around it, the flow field that is predicted, there is no guarantee that it will satisfy the conservation of mass. In many cases, you can get away with such broadband errors. In many cases, this will not be acceptable to the people who are the downstream users of these surrogate models, right? Secondly, there's this issue of interpretability. So like I said, if you just stack bunches of neural networks on and try to fit your data, you might get a good solution, but you don't really know why it is a good solution, and you don't really know when it is performing poorly. So these types of things are important to quantify in an application, right? Because an application has a potential loss associated with it, so we don't want to trigger that. And of course, 3 and 4 are limited are related to point 2, where if you have a model that is in some sense getting rid of your understanding of the physics. You had a set of PDEs which gave you some understanding of the physics. Of course, you did not understand everything, so there was some epistemic uncertainty, but now you've replaced everything with a neural network or a Gaussian process, and in such cases you don't really know anything about you know things about the physics, but you're throwing it away in some sense. So you're actually increasing the uncertainty of your forward model. And finally, with most state of the art modeling methods out there, there is very little a posteriori error analysis, which is a big problem with especially things like neural networks, right? And I've sort of mentioned this over here. Um, limitations lie in a spectrum. If you're using a neural network, you know that the error analysis is that one paper everybody will cite, Chubenko's paper on on how you can approximate a function, or there exists a neural network that approximates a function, but that doesn't tell you anything about whether your particular task is being approximated properly. So that's why what we try to do here in our group is to address these through our domain expertise and come up with, in some sense, better architectures altogether, better neural frameworks. Okay, and so at this point you might be having a question where you would be like, oh, but have you heard about physics informed neural networks, which are also very, very popular nowadays, right? They are a very easily utilized strategy where you can embed constraints into your framework. So what this framework basically does is you have a loss function that's given by your desired function approximation. So you want to minimize the error between an input and an output where the output is something you desire, and then you add a penalty term to the loss function, which over here they call it an unsupervised loss. But this loss function, for example, could be penalizing a disagreement for a set of equations. So f theta could be a PDE, right? And then over here, f theta x and y are basically the data mismatch. So the advantage of something like this is that you can embed very easily whatever understanding you have about a particular physical process into your learning, and at least guarantee a soft agreement with that during training. Of course, this is only a soft constraint embedding. So from personal experience and from anecdotal conversations, I have seen that when your problem gets very complicated, a simple addition of a PD based loss that the pin uses does not lead to satisfactory results for real problems. So if any of you visited SIAM CSE, I don't know if the SIAM talks are still online, but if they are, you might want to check out a talk by a group in the US Army where they actually used a pin for simulating a helicopter, and they ran into some really really interesting problems. So it's a very, very useful. It was not Berger's, thankfully, after all these years. And it was not flow around the cylinder either. It was a real problem, and they give a very honest assessment of these soft constraint based methods over there. So I can find it for you if you're interested in reading up more about that. Send me an email or just contact Boumediene. I can have it for you after that. Okay. And so recently there have been some methods to actually improve this PD based constraint as well. So for example, in MIT CSAIL, they've actually done like a transfer learning or a retraining of a few layers of the neural network, so that even during testing, they minimize the PD residual, right? So previously you would train a network and not train on and not touch it anymore, just use it for predictions. Over here, if they're doing testing, they know that the test data also has to satisfy the PD residual, so they minimize the PD residual during testing as well, and then slightly update the weights of the network and then make predictions with this retrained network, and they see that they get a better results. This is an interesting paper, might be of use to some of you. Okay. So what do we want to do? We want to in sort of a slightly like a poor Western type of movie title. I'm going to say I'm going to put the science in scientific machine learning. This is not a knock against the excellent papers that come out that claim to do scientific ML, but what our group or my collaborators we really revel in is the fact that we don't look at soft constraints for embedding science into our scientific ML, but try to identify, structure your data, and then leverage or to build algorithms and architectures that actually embed them into your workflow. So, and this is not easy, unfortunately. So there are some examples that you may be familiar with. Excuse me. So the first is um, operator inference. So, if you have data set, if you have a data set, instead of actually fitting a neural network or a data-driven method, can you fit a system? Oops, sorry. Which, for example, could be learning a PD, right? We're learning the terms of the PD or learning the terms of the OD. So the first 2 points over here are algorithms that extract systems from your data. And this is also not easy because often your data is not in any sense ready to be to have systems extracted from it. It could be extremely poor data, or it could be data that is completely disorganized and sparse. So in some such cases, maybe these methods 1 and 2 are not super useful, but there exists a class of problems that are quite nicely solved by them, right? Then point 3 talks about certain novel neural network architectures which actually embed properties within them. For example, the fact that they can learn a Hamiltonian, the fact that they preserve the symplectic relationship, and Hamiltonian neural networks were brought out by Greediness at Google, and symplectic neural networks were actually pitched by both Kavrakidis and Karnidakis members, and then their collaborators, of course. So what this tells you is that if you know that the dynamics that you're observing preserves a Hamiltonian, then you could construct a surrogate modeling strategy that guarantees that your Hamiltonian is conserved. So this is obviously valuable. And then, if you know that the function approximation that you wish to do is invertible, can you guarantee that your neural network is invertible to always, preserve that relationship? So these sort of ideas are quite interesting to us, and quite interesting to very many domain scientists, because they are definitely appreciated if such properties are respected in the process of their training and inference. So what we will be looking at today is a couple of examples, couple of test cases where we do try to understand the structure in the problem, and then build that into our surrogate modeling strategy. Okay, so the first case is work that I have done with um, Josh Burby and Chi at the Los Alamos National Laboratory. Josh is the Feynman Distinguished Postdoctoral Fellow at Los Alamos. Chi is now very recently a scientist over there. He was a postdoc when we did this work. And this work is published in this paper. This project has been funded by the SciDac Rapids Institute in the DOE. And what we do in this particular project is actually relevant to the plasma physics community. In particular, if some of you might be familiar with this diagram over here, but what this is showing you is a donut-like structure, right? That is obvious. But this structure actually represents a tokamak, which is a plasma fusion device, which contains plasma basically, and these lines that you see over here are basically magnetic field lines that kind of um, that basically traverse the plasma in a circumferential direction. And the idea is that uh, these field lines, as they complete a rotation of the entire, or complete a revolution of the entire torus, you can construct this sort of cross section, which tells you a lot about the behavior of these field lines, in that a particular point on this cross section, if there is a field line that is going off in the normal direction to the cross section over here, if you track that field line and see where it's intersecting the cross section again, so you have a field line that sort of traverses the entire torus and comes back and hits the same cross section. If you mark that point, and if you do this several times, you generate what is called a field line Poincare map, right? And this, for plasma physicists, is very important to to basically understand regions of their torus where, for example, there is no field line crossing that cross section. It also helps understand whether a disruptive event is about to occur. So you have disruption events that happen in the operation of fusion reactors, which are currently the biggest bottleneck in their successful adoption as a profitable power generation uh, 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 process or profitable power generation approach. So uh, we want to be able to predict the Poincare map of a particular torus with particular set of operating conditions, and currently that is quite expensive, so we want to build a surrogate for doing that. Okay, so let's go over how it's done currently, right? So just to introduce a little bit of notation, so this entire domain is called Q. It's called a toroidal domain, or for the torus, right? And then you have a poloidal cross section, which is just this guy over here, P, and there is a magnetic field B on Q, and when it intersects with P, you get this diagram, and we want to predict this diagram using machine learning. Okay, so currently the way you actually construct these cross sections is by basically using like a field line integration method, which uses some sort of RK method, right? So you have a dynamical system which is constructed to take a point in P with some field line parameters that are governed by the operating conditions of the tokamak, and then just evolve that trajectory across the torus until it crosses the cross section again, and then you mark that point, and you go on and so on and so forth. Okay. And then what you do is you specify multiple initial conditions for X and generate, in some sense, multiple points where they intersect, and then you get this cross section. Okay. So and so the idea is that for this particular problem, right, if you make a certain set of assumptions which are easily satisfied in the actual operating condition of a torus, of a plasma reactor. So if you say that if B has a nowhere vanishing toroidal component, right? So if you basically the B, there is always a perpendicular to the cross section component of B, and that the magnetic field is always contained within this torus, then there is a mapping, a smooth mapping from the cross section to itself that is known as the Poincare map. So to visually show this, you know that there is a particle, or there is a point over here that you can integrate across around a field line and reach the cross section again. What it's saying is that, what this statement is saying is that if B always has a component that is perpendicular to the or always has a is not zero, basically. If B is not zero within the torus, and that B is always contained within the torus, then you can actually construct a function approximation from an initial condition to its next point on this cross section, and that is the function that we will approximate using a machine learning framework. Okay. So please stop me if this is not if this is confusing, or if you want me to go through this again, right? So this is called our Poincare map. Okay. So it's got some really cool properties, and these are the properties that we will sort of embed into our ML framework, right? So for example, the first property is that the magnetic flux through a subsection of that cross section is the same as the magnetic flux of the points that that were initialized over there and then traversed the entire field line and came back to the cross section. So U is the initial conditions, phi of U is where the initial conditions end up, and the flux through these two sort of sets is the same. And this means that phi is actually a symplectic map. Okay, so it's a volume preserving map, and the field line flows in, again, under these assumptions, are then Hamiltonian. Okay, so what do we want to do? So if we have examples of the Poincare map, right? And how do we generate examples? We generate examples by actually doing the field line integration. If we have examples of the Poincare map, then we can actually approximate phi by using a Hamiltonian neural network or a symplectic neural network. That and that is what we will do. And if we do have access to this Poincare map, then we don't have to do these costly field line integrations anymore. We just select any number of points in this region, apply a phi on it, and we immediately generate their next intersection with the cross section, and we do it multiple times, and we're in the money. So and so the challenge over here is obviously that you have to ensure that this approximation is symplectic. Okay, and that's what we've done over here. We've built a new class of symplectic neural networks to guarantee this. Okay. So there are certain candidates for the choice of phi, right? So firstly, we looked at the Hamiltonian neural networks by Gredness at Google, but there are a couple of reasons why we discarded them. They don't exactly satisfy symplecticity, and finally, what this method does is it actually learns the Hamiltonian, but you still have to end up needing a numerical integration method. So we still have to integrate across the field line because we will have stability issues with the size of the time step, right, in some sense. So this had to be discarded. A modification to the Hamiltonian neural networks for these symplectic recurrent neural networks, where they just used a symplectic integration method rather than a RK4 based integration method to guarantee symplecticity. And that lets you take slightly larger time steps, but you still have to integrate. So we don't want to integrate at all, right? And finally, there was a new architecture proposed by Jin et al. And with George Kanidakis, and this is called the Simpnet Architecture. And this did not require any symplectic integration. It directly was able to learn a map phi, and so this was a viable candidate. So we decided to dig this a little further. Okay. So very briefly, I'll just introduce what the Simpnet is. So the Simpnet is a architecture which composes a set of these triangular operations on your input to obtain, and these triangular operations basically can be decomposed into a combination of linear up modules and down modules. That's what they called it in their paper, right? And it basically looks like this. The goal of any optimization algorithm would be to learn the elements in S2, S1, Sn, and so on and so forth. And so you would combine up and low operations to fit a map from the input to the output, right? This would be a linear symplectic neural network, which may not be expressive enough for your particular data set. So they also pitched an activation module. So just like in a neural network, you'll have activation functions on your hidden layers. They called it an activation module, which looks like this with a sigma tilde over here, which has learnable parameters k, and sigma is generally the time hyperbolic, if I'm not wrong, or sigmoidal activation. I'm not sure, but you could have a linear up, a linear down, and then a non-linear up and a non-linear down, sort of concatenated with each other, and you can choose your various combinations of composition to obtain this symplectic neural network. Okay. And so we picked up the architecture that they found was best for a particular problem, right? So and compared it across different types of frameworks. And I'll show you, we also pitched our own framework very soon that was able to outperform the Simpnets, right? So the first problem we looked at is something very canonical. I'm sure all of you have played around with this at some point in time. So you have a pendulum system which has a very simple Hamiltonian given by this expression over here, y square by 2 minus cosine of x, and then you can integrate the system by using RK4. So you can generate training data for this particular system. In this case, we are just assessing the ability of networks to basically learn Hamiltonians, and we're not really looking at the Poincare map. For the Poincare map, our h would in some sense be 2 pi. It would be one entire revolution. So so the so the Simpnet paper by Jin, they proposed two architectures, the LA Simpnet and the G Simpnet, which were basically slightly different combinations of the linear modules and the nonlinear modules. And the LA Simpnet they showed was better, right? And so you can see over here, they generate training data only in this dotted region over here. Uh, uh, for using the Hamiltonian, and they actually test it on a completely different region, and they're able to get a really nice performance by using a symplectic neural network, because again, when you have hard constraints built into your neural network, there isn't a guarantee that you will extrapolate perfectly, but there is a better guarantee than just using like a regular neural network. And you can see over here with the standard Hamiltonian neural network that the people in Google proposed, if you are generating training data only where my mouse cursor is, but testing it outside, you were going to get basically a diverging type of behavior, because you don't guarantee symplecticity, or you don't guarantee that your Hamiltonian is learned exactly. So this, in some sense, is a pre-validation where we realize that okay, the Simpnet architecture is probably the best way forward, but we decided to see if we can actually improve it even further, right? And the way we did that is by finding this rather obscure paper by Turev in 2003, which said that if you define a Hennan map given as such, where if you have two coordinates x and y, the Hennan map basically adds a constant to y and then defines a scalar potential function as a function of y, which you can take the gradient of and subtract x from it, and that becomes the new y. Then this map is guaranteed to be, and or so four compositions of this map according to this theorem will guarantee a symplectic mapping. Okay, so we know that if we can leverage this type of structure within our feed-forward neural network, we can guarantee a symplectic map by design, right? Similar to the Simpnet paper that I just talked about. So after we found this paper, we basically decided to do exactly that. So over here, you can say that you can construct V to be a neural network, okay, which is a function of one of the inputs to the neural network, Y. And with these modern machine learning frameworks or software, computing the gradient of a neural network is trivial because of auto differentiation, autograd. And eta would be also an output of, eta would just be a constant. It would not be a neural network. Eta would be a constant that would be fit by our optimization. So what basically we came up with is something called a Hennan neural network architecture, which composes four Hennan maps together, where for each map we have a fully connected neural network that predicts the potential, and then a gradient operation on the potential actually is used to compute the the output, and this constant eta is also, it's not a part of the neural network, but it's a constant that is fit during optimization. And then composing four of these guys together gets you one, what we call a Hennan layer, right? And this one layer of the Hennan net is able to guarantee symplecticity. And of course, you can compose multiple layers on top of each other now to increase the expressivity of your function approximation. But by design, we have a guarantee to respect symplecticity, right? And then we go back to the pendulum example and actually compare the Hennan net and the Simpnet. Simpnet, again, we picked up the best architecture and the best hyperparameters that were reported in that paper, right? And we were able to see that we are able to get a much better performance than the symplectic neural network with fewer trainable parameters. And our training also happened faster because of that, because of the fewer training parameters. And just to assuage any fears you may have that this was a one-time fluke, we also performed like a randomly initialized set of hyperparameters, neural networks with randomly initialized set of hyperparameters, and we trained all of them together in parallel. And we saw that in general, you are most likely to get a Hennan net that outperforms the Simpnet just by binning the performance on the test data and comparing the two, right? So you can see over here that the median value of the HannonNet validation loss was much lower than the median value of the Simpnet validation loss, right? And this is like randomly initialized neural networks. There's no sort of optimal hyperparameter search or anything that we are doing over here. Okay. And so what does this mean? This means that the architecture that we proposed outperformed the symplectic neural network. So we could go ahead and actually use it to now learn Poincare maps, right? Previously we were just learning a symplectic map from time step t to time step t plus h. H was just 0.1. Over here h now becomes 2 pi, which makes the problem a lot more difficult, but this is the problem we want to solve from our applications perspective, because we want to come back to the poloidal cross section in the torus, right? And the problem with this is that firstly the time step is large, so the problem is more difficult naturally, right? And the second thing that happens is there is this problem with deterministic chaos, which happens when your time step is large, especially in this type of problem where you have separation of trajectories that are controlled by the length of the time step h, right? So we definitely need a lot more muscle power in our neural network. We have to use more layers, more neurons, a lot more training data to actually train this network. So for example, we first want to learn the Poincare map of the pendulum. And so we restrict ourselves for initial data points to a region of r less than 0.3. R is the radius, p square plus q square under square root. And we tested on a much larger domain. And you can see that if you compare the Poincare plots for the Hennan net with seed points on all these locations, and that by Rangakotta over here, we get a qualitatively similar response. In particular, you get these white regions where you don't have any field line intersection, which is exactly what we desire, right? So they are quite close to each other. Then we can start now making our problem a little more complicated, right? So this problem over here is a perturbed pendulum. So you also have a parameter that goes into that pre-multiplies cosine x and a perturbation on the right hand side. And I don't have the parameters off the top of my head over here, but we set them, we fixed them in this problem. And they give rise to this really intricate Poincare plot. And again, using the same excuse me, same settings as the previous example, we are able to again qualitatively obtain the Poincare picture over here. Of course, we do this much more faster now because we don't have to do any field line integration using RK4. Okay, now the next step is obviously to look at problems that start approaching our application. So the plasma physics community has spent a lot of time in coming up with these sort of idealized Hamiltonians, which start mimicking the nature of the Poincare map of a real torus. So for example, this is a particular Hamiltonian over here, which is called the RMP Hamiltonian, or the resonant magnetic perturbation Hamiltonian. And you can see that the training data that we had to use then became quite complicated, right? So this was the input training data, and this was the output of the training data. We had to generate a lot more training data. We had to go up to 400,000 points, right? And then once we did that and we learned a Poincare plot, we were able to again, learn this this behavior of the Poincare map quite nicely, where you can see that you get these islands over here where the field lines don't intersect. And this island type of behavior is something that is a hallmark of this particular Hamiltonian, right? And interestingly, you will see that if you start your seed points, so in the computation of your Poincare map, if you start your seed points on an island, you're supposed to always remain on the island. So this is called the island chain behavior of this particular Hamiltonian. So over here we are starting our initial conditions all across, the cross section. But if we started only at the island, then you should never leave the island. And our approximation to phi, our Hennan neural network, actually demonstrates this property just like a numerical integration scheme does with a small time step. Of course, in our case, we don't have a small time step. We directly find the next intersection point. So this was something that excited us greatly, right? And when we increase the number of seed points, well, sorry, not increase the number of seed points, but when we actually compute the forward propagation of the initial condition using the application of the neural network 10,000 times. So in this example, we start a seed point and we pick a seed point and we apply phi to it 1,000 times to get 1,000 sort of crosses on the map, and then we use a certain number of seed points to do that. Over here we just increase that 10 times, so we apply phi 10,000 times on a seed point, and you can see some really very interesting features emerge from the application of these approximate Poincare maps. So the first thing that you will see is that the picture is very dense, but you also see these filamentous structures that that it's basically a zoom up of this region over here, that show how the Poincare map approximation is actually prone to keeping a particular field line in a particular region, right? As against letting it just randomly go off into other regions of this cross section. So when we actually decided to investigate this further and we computed the Fastly-Lyapunov exponent, you can see that dark areas imply regions where the application of phi tends to keep the field line in that area itself. Whereas if we apply phi to a region here, then it's much more likely that the next point of intersection is somewhere completely different. So what that means is if applications of phi are made to a certain point that end up in this region, they stay in this region longer. So a link to the application is or to the plasma physics application is, this is useful for actually identifying entrainment characteristics for plasma. So when your field lines are actually entraining plasma within your torus. So in these regions, you would have plasma entrainment in this structure, and that is of use to know while you are setting up your operating conditions. Okay, so so in practice, you may ask me, okay, now you've shown me results which are in some sense idealized because you've actually the form of the Hamiltonian. In practice, what would happen is you would have the operating conditions of the plasma. You would have the magnetic field, right? And the magnetic field distribution in the plasma would have to be used to actually compute the Poincare map training data, and then you would fit a surrogate model for the Poincare map to generate these types of images. So that's kind of the ultimate application of this technology. Okay, so we are currently investigating a bunch of extensions to the Hennan nets. We recently got results that are quite promising. So one easy extension is actually preparing it for adaptive time steps. So we could generate Poincare maps, but we could also generate field line following trajectories, and that can be accomplished by making the potential that I was talking about in the Hennan map a function of not just one of the coordinates, but also a parameter. It could be, for example, the time step, right? We're also looking at how, for example, we can parameterize the potential as a function of time in case there is a time varying magnetic field, in which case if there is a periodic nature to the behavior of the magnetic field, we have to include some periodic transformations. into the neural network to account for this, right? And finally, because in some sense, what we have basically done is introduced a new symplectic map. We can actually compose an invertible map with these coordinate transformations to learn sort of autonomous flows. So that is also something that we are looking at, right? Okay. So now I will move on to my second case. If there are any questions at this time, maybe we can quickly go through them. Are there any questions? Any comments, feedback, criticism? Anything is welcome.
Do you have a reference to your work on Hennan maps?
I'm sorry, do I have a reference to this work?
Yeah, it's really interesting. I'd like to read more.
Yeah, so it was right at this front. It's this paper over here. I can we can either take a snapshot or I can.
Yeah, I've got it now. Thanks.
I also have a question. This non-map approximation is by design is very good when for example, you have Hamiltonian flow like kinetic energy plus potential energy. And if I remember correctly, it's supposed to be very bad when you don't have the structure. So if you test it on an example when your Hamiltonian system is not kinetic plus potential, do you still get good results, or it fails as it should?
That's a good point. We haven't tested it. I'm gonna slack my collaborators right away.
Because if you look at the proof, it's done in 2 steps. First, you approximate kinetic energy and plus potential, and this is kind of effective. And then you do very ineffective approximation for general case. No, so this particular Hennan, it could still work, but it could be that it is built in that Hennan approximation work for certain large class of system, but not for all. Okay. No,
that's a good point.
But it would be interesting to check. I don't know.
Yeah, okay. I think that. Thank you for bringing that out. That is definitely going to be.
Yeah, that's Dima, by the way. Dima 2I, if you are referring to. Yes.
Yeah, because it's my theorem you refer to, so that's why I'm asking. It's not the criticism. Okay.
Sure. Okay.
Yeah, thanks, Dima. Yeah. Yeah, and there's also Tom Bertalan. Did you want to say something?
We have a paper in Chaos which is very similar to the Sam Gray-Dunnis Hamiltonian neural networks paper. It's not a big thing. I just wanted to put that out there. Okay. It's we have an autoencoder which imposes that in the encoding layer, the dynamics they conserve some Hamiltonian quantity.
I see. Cool. Yeah, I mean it's a fashionable topic. There's a lot of people. I think Kavrakadis also had a paper recently where they use Gaussian processes for.
Yeah, Kavrakadis is my boss. Yeah. So.
Oh, great. Yeah. So, all right. So now let's go on to the next. So I also work with Yanis. It's a fun experience, I'm sure. So the second test case I'll be talking about is stuff related to learning stochastic processes, in particular stochastic differential equations, or and identifying stochastic differential equations. So this stuff is not online yet, but we are working on this. We should be submitting it soon. This is work that is done with Dr. Duan at IIT Chicago. So and Yubin, who is a grad student at Johns Hopkins, and Yanis, of course, who is also at Johns Hopkins. And what we do in this particular problem is actually use generative machine learning models to learn densities for stochastic processes, and then use these densities to extract some quantities of interest. Oh, actually, I should forget. There's another person here who did contribute results to this. I forgot to add his picture. His name is William McClure. He's a master's student at IIT. So yeah, apologies for that. Yeah, okay. So again, I'm sure this crowd should be very familiar with SDEs, but this couldn't be a quick crash course for people who do not. So the idea here is that in comparison to a standard ordinary differential equation, your stochastic differential equation is driven by some noise, in addition to something called a drift quantity. So the mu over here is a drift. It's a deterministic quantity. And then you have a noise term. Most SD applications or SD studies will prescribe this noise as a Brownian process or a Gaussian process and assume it to be additive, right? That makes things much easier, right? And so when you simulate this from initial conditions that are sampled from a distribution, you can actually basically do like a Monte Carlo type process to find the evolution of the density of X over time. So, you know, like let's say our X at t equal to 0 is coming from a Gaussian distribution. So you sample from that, you solve this system of equations using a SD integrator, and you get a path, right? You can do that again, get another path. And so at each time you will get the locations of different paths. So you'll get different paths and where they are in X, and then you can construct a density from that. Or if, for example, your formulation has been set up properly, you could construct a Fokker-Planck PDE, which then you can solve to actually analytically get the evolution of the density, right? When you have a Brownian process and your Fokker-Planck PD kind of becomes not very difficult to solve. It has this formulation over here. So you have a Laplacian that takes care of the diffusion, right? Now, what we are interested in this problem, but not as interested, because what we want to look at is a case where the noise is not just Gaussian and additive. We also want to look at a non-Gaussian noise component, such as a Levy process, right? So a Levy process causes these sudden jump phenomenon. Sorry, my cat is yelling at me. Yeah, and in this case, the problem becomes something like this, where the Fokker-Planck PDE now ends up having a non-local or something like it becomes an integral differential equation. You have an integral term over here that becomes very painful to compute numerically, right? Compared to a standard Laplacian over here, right? So if you assume that the Levy process is just additive in nature, then you do get lucky. You still have integral term over here, but you get a fractional derivative, and then there are some techniques that can help you compute that efficiently. So our goal over here is to bypass the solution of the Fokker-Planck PDE when using by using a surrogate model specifically. And more importantly, we want to learn densities from paths or data that is arbitrarily available without making any assumptions about whether it's coming from a additive noise Levy process or a Brownian process or whatever. We just want to learn the density directly from data. And so people who have been, so this is an example of, the difference between like a Brownian process and a Levy process. So, if you zoom in, then maybe there is not much difference between the two, but over a long period of evolution, you get these sudden jumps that happen in the Levy process, and that is something that makes that Fokker-Planck PD look quite ugly, right? So, and there are many applications for this. For example, this is a very cool paper where there is some data, and we have access to this data as well. There is some data that was obtained by digging the permafrost in Greenland and parts of Scandinavia, and measuring the calcium signal in that ice core. And the calcium signal, the log of that calcium signal concentration is directly correlated with the, negatively correlated with the global temperature, right? And so in this paper, Detlefsen found that you could model the evolution of the evolution of the calcium signal using this nested stochastic differential equation. And it wasn't a differential equation with simple Brownian noise. It had a Levy process in it with certain hyperparameters, right? What we want to do is now learn such systems. Well, now you might ask, okay, what happens after you learn this system, right? So after you learn this system, there are certain tools available there to compute quantities of interest, such as mean exit times or transition probabilities that help you predict whether, the state of the environment that you're in right now. What? Sorry, my cat. Is stable, or is there an imminent chance of a jump to another state, and that is something that we want to accelerate by using scientific machine learning. Okay, so and you can see over here there's a bunch of text on this slide, but classically, we if you want to obtain densities for the for a particular sample path data, you would have to do either some Monte Carlo type technique where you would simulate the stochastic differential equation. This is assuming you have access to the system, obviously, right? In the ultimate application, you don't have any access to the system, but you would simulate your SDE multiple times by using randomly sampled initial conditions, and then you would construct histograms of the density at different slices in time, right? And that would be how you would test the evolution of the underlying PDF. But obviously, this thing is not scalable, because if now your sample path is traversing a very high dimensional space, right? Then it becomes difficult to fit these histograms. You have to sample a lot, basically, and it becomes quickly costly. Okay. So to summarize, we want to learn a time varying density directly from this sample path data, right? And what we want to do is we want to use this approximated density to extract essentially our system, our SD. Okay. And so there are certain methods that, again, in the machine learning community, not the scientific machine learning, the machine learning community, which were a good fit for the work that you want to accomplish over here. So there are some ideas that this group in the University of Toronto is doing, which is with David Duvenord and Lars Ruthoto at Emory. So they've been pitching the use of neural ordinary differential equations, right? And more recently, they have been migrating these to neural stochastic differential equations, where now you have a neural network that is so in the neural ordinary differential equation, you have an ODE where the right-hand side is a neural network, and then you integrate using a numerical integrator during the training and the testing. In the neural SDE, now you have a framework where the drift and diffusion are given by neural networks, and you use a stochastic integrator like Euler-Maruyama to integrate during training and testing. However, they are limited to Brownian process with additive noise because, like I said, you cannot train these frameworks within an equation-based formulation if you have a Levy process, because then you would have to do a non-local integration during our forward and backward propagation. And as far as I know, there is no automatic differentiation for fractional derivatives. You have automatic differentiation for integer derivatives, obviously, and because you can use the chain rule of calculus to differentiate through a neural network, but not for a fractional derivative, or not for a like an integral differential sort of term. So George Kanedakis also proposed something called the fractional pins, but if I'm not mistaken, in that paper, the fractional term in the pin was computed numerically and not through automatic differentiation. So we want to stay away from equation-based frameworks because of this bottleneck of actually computing the fractional term. And in many cases, we don't even know what that term is because we don't know the system. We want to learn the system. Okay. So there was another paper out there, out on the archive recently, where again, from George's group, there was an idea to use generative adversarial neural networks, which can learn these densities in an equation-free fashion, right? I personally am not a big fan of GANs. If there are any people in the audience who are on my side, I'm happy to buy you a cup of coffee or something, because I have tried training GANs on many problems from simple to complex, and it's just so brittle when it comes to training these frameworks that I don't really have faith in GANs, but that's just a personal experience. Maybe I'm not doing something right. So we wanted to do something different since someone else had already done it, right? So, but they saw that they had a lot of trouble training. Their accuracy wasn't that high, and also they didn't show it for a system which had non-local terms. But in principle, they could have done it if they wanted to, because GANs do not, they just need data. They don't need a functional form. So. All right. So, and the third one was, again, there's a Fokker-Planck fractional pin, like I was talking about, but again, it required this numerical computation of the fractional derivative, and we didn't want to do that. We wanted to just, in some sense, use backprop and automatic differentiation. So what we decided to do was use normalizing flows, which are, a technique analogous to the use of generative adversarial neural networks. So for those who are not familiar, normalizing flows are basically a type of neural architecture that learn transformations from a known latent density. So in this case, you know that there is some latent density which is Gaussian, and a target density, which in our case, the target density is being observed by looking at the sample paths. And the normalizing flow learns these compositions of functions f1, f2, all the way to fi plus n. So the neural network actually goes into what this f is, but the end result is that you basically have a bunch of affine transformations from that are composed with each other to go from the latent density to the prior. To go from the latent density to the target density. Okay. And so what is the assumption over here? The assumption over here is that there is a transformation that exists that takes you from the latent to the prior density, and this transformation is invertible and it's one-to-one. So one sample from this latent corresponds to one sample from this target. Okay, and this t over here is something that we have to learn, the transformation, right? And assuming that t and t inverse are differentiable and invertible, then you can also set up this relationship for the probability, right? And this is also a volume preserving type map. So it guarantees that the integral of your probability in your domain, whether latent or target, is 1. So by design. So you have this expression over here. So all that is left for us to do is prescribe a form for t that has some trainable parameters in it, and that you can learn using a log likelihood minimization. So what does that look like? So and so we'll get into that. So you can also compose multiple different transformations together, and it's very simple like this. And you can easily compute the determinant of their Jacobian like so by again composing the maps together. And so the ultimate loss function for this framework is given by basically taking the natural log of both sides of this equation 18 over here. So you want to minimize the negative log likelihood of p of x. So you basically minimize negative log likelihood of this side, negative log of this side. And once we do that, we basically train for t to allow us to then arbitrarily sample from this latent density and go to the target density. Okay. So what do we specify for t? So there are many different ways to specify t, right? So the more, I think the easiest way to, for example, if you were to code this up over your weekend, if like me, you have no social life, you would probably use an affine transform, right? Which is an easy way to guarantee invertibility and also and find a Jacobian that is extremely easy to evaluate, right? You don't want to evaluate a Jacobian by actually computing the derivative of the determinant of this Jacobian, which could be quite costly. We want to make sure that it is just a few floating point operations. So by prescribing a transformation that goes like this, where a certain set of the input sample is held preserved, and the rest is transformed by this affine transformation. So you have a translation and a scaling. You can guarantee invertibility, and then after you get z from x, you could compose another map on it but you could deploy some perturbations in between to ensure that your first small d variables don't always stay the same. So you can provide a perturbation that's quite common. So what does it boil down to? Mu and nu over here are basically the neural networks that are a part of this architecture, right? So how will the forward operation work if you're trying to sample something or go from the target to the latent? You will give it x of 1 to d to one neural network, and it will compute mu, and you'll give it to another neural network, or you can have the same neural network compute mu and nu. That's also possible. And then you will perform this operation on the remaining components of this multidimensional state, and then perform this update, and then the first d components remain the same, and then you perturb and you do the same thing with another set of neural networks. So and by composing these two together, you now build a transformation between latent space and target. Okay, the determinant of the Jacobian is only required when you're training, but during testing it's not required. Okay, and people who are familiar with normalizing flows will will recognize this to be like a time varying analog of the real non-volume preserving flow, which is given by this ICLR paper, very highly cited in 2016 or 15, one of the two. And we've recently extended this to using more modern techniques for normalizing flows, such as neural spline flows, which I don't have a slide about over here, but neural spline flows are basically, instead of having affine transforms over here, they have rational quadratic transforms between density to density, and that is more expressive, more accurate, more sample efficient. So, but in principle, the framework we are setting up here is agnostic to the choice of the transformation T. Okay, so let's look at how this performs for a couple of test cases. So the first example over here, we directly start off with a problem which has a Levy process. So it's only got anomalous diffusion. It does not have any Brownian noise. And what we do over here is we solving the Fokker-Planck equation of this guy is not trivial at all. So it's very difficult. So what we do is we generate training data from the solution of these SDs using Euler-Maruyama, and we use 500 initial conditions sampled from a Gaussian for both X1 and X2 to solve this and generate training data. We don't have access to the Fokker-Planck, and we could construct a Fokker-Planck for this thing, but it would be extremely difficult to compute. We require some special numerical methods to do that. And you can see that if you look at the evolution of the density over time, so initially you have a density that is coming from a, like a Gaussian with zero mean and isotropic variance. So it kind of looks like this. But over time, you have more stretching in one direction compared to the other. And so the top row over here is the true evolution we just plotted the SDE paths. Okay. And the bottom row is the samples from the density that we learned using the normalizing flow. So you can see it's matching this sort of behavior where you have sort of like anisotropic stretching. A second example that we look at over here is a lot more interesting. This leads to a multimodal distribution evolution. So again, the initial condition is just a Gaussian blob in 2 dimensions. But because of this formulation, again, we use 500 initial conditions and solve them with our SDE. You get a behavior like so. So on top, you have the training data that was used to generate, to learn the transformation. So you have a Gaussian that then turns into this 4-mode, 4-well system. And over here, you have a normalizing flow that's basically predicting the same thing. So you're able to learn a time varying density using the normalizing flow. And so that gets us halfway to our solving our target problem, which is learning the density. And once we have the density in the form of a easily sampled Gaussian, because essentially what the normalizing flow is doing is learning a latent space Gaussian from which you can sample, but then the samples will end up coming from this multimodal data informed distribution. So we can then perform Monte Carlo using this approximate density quite effectively. Okay. Just to sort of close the loop, we do actually compare against a regular system for which a Fokker-Planck PD is quite easy to construct and solve. So here we only have a Brownian process, so we don't with additive noise, and we don't have any anomalous diffusion. For this guy, when we actually predict the evolution of the PD using the Fokker-Planck equation, that's the first row over here. So you get this sort of this wake behind this density peak that is evolving. We're able to, again, qualitatively get the same behavior. Again, since we are not really using a lot of data to train these methods, we are able to, from just 500 data points, we're able to get the similar type of evolution, which I think is quite nice. And there is some error. Obviously, these methods are, after all, still approximate. So we're still working on these to improve this potentially. So, but you can see qualitatively the nature of the density evolution is being extracted quite nicely. So, okay. So so now I'll just quickly I'm close to finishing up this talk. What we want to do is now use this density, right? We fit a density, right? Now what do we do with this density? So we want to extract, for example, the SD. The first thing that we want to do is we just observe sample path. We don't know that it's coming from an SD, but can we extract a suitable SDE from this, right? And this is the work that was done by Will McClure. So there's this paper in Physica D by Dr. Duan and Yubin for actually extracting the generator of a particular function if it has been generated by an SDE, and this relies on us actually knowing what the density is. So previously in this paper, they had computed this density using the Fokker-Planck PDE, and then had learned the generator of the Fokker-Planck PDE using this Koopman type framework. However, I mean, having access to the PDF is a luxury, and what we have done in this work is in some sense close their loophole, where we have said, okay, now we can use data to not just learn the generator, but also learn the PDF. So, or to learn the PDF, and then after that learn the generator. So and why is this important? So when we again, there's a bunch of equations over here. I don't want to spend too much time on them, but essentially, if you assume that your okay, so if you assume that your generator for a particular SDE is coming by setting the value of f, or the generating function, to be x, then you can perform this expression exists. Okay, you can check the reference out, from which you can extract just the drift term directly. Okay, so by assuming the form of f, you can apply this expression and extract the drift and diffusion terms out of the SDE. So over here you have specifying fx of t equals to x gives you the drift, and when we set it equal to x square, we can get the diagonal terms of the diffusion. Again, this is assuming that we have a simple case of just additive Brownian motion. So when you have Levy processes, this thing gets a little more complicated, and we're working on that at this moment. But at least for a regular Brownian motion type assumption, we can obtain these approximations for the different terms in the SDE. So we checked it out for a simple double well system where we have a stochastic differential equation that is evolved using this expression. It's just one-dimensional x. It's not two-dimensional. And you can see as you sample from a, maybe in this case, I think the sampling was from a uniform distribution between minus 2.5 and 2.5, you end up with a double well evolution. So some paths will end up in one well over here, and the other paths will end up in another well over here. And by using a normalizing flow to learn the density evolution over time, you can actually recover an approximation to the true drift, like so, and also the true diffusion. In this case, the diffusion is easy to compute. And so that is something that we are excited about, in that you can identify stochastic differential equations from data by using normalizing flows. And of course, on top of this, you could layer on sparse regression type ideologies to identify these terms over here, if you believe that they are generated by some polynomial functions. So that we haven't done that, but this is an interesting way to extract the qualitative behavior of your data set in the form of an SDE, right? So and we are working on several extensions to this. So the last 5 minutes was definitely work that was done in the last couple of weeks. So we still have to refine that stuff. But some things that we are working on are, like, for example, increasing the quality of the normalizing flow itself to make it more sample efficient for our particular task, and to scale it to higher dimensions. For example, we've already deployed dual spine flows to see that it does a much better job, but we didn't use any of those in our results today. And also we want to see if we can improve the optimization of these neural of these normalizing flows by potentially using some more informative sampling to compute our log likelihood during the optimization process. And in terms of our application engagement, we are currently deploying these to construct stochastic turbulence closures. So that is something that interests me. And also, obviously, another thing that is left to do is actually compute those transition probabilities that I was talking about. But now that we have access to the density, or an approximation of the density, and then an approximate stochastic differential equation, then you can use classical techniques to actually compute these transition probabilities. So that is still work that is in progress, and hopefully we'll have some of those results maybe for a future talk. And yeah, so I think I would like to stop there, leave up the slide for some acknowledgements. And if you have any questions or you want to yell at me, it's all welcome. I'm happy to help you out.
Yeah, thank you very much. I think we'll applaud you, not yell at you.
Yeah, thanks. Yeah.
Thank you. Yeah, any questions?
Beginning with comment. This is a beautiful talk. I didn't understand the topic first because I'm not familiar at all, but you surprise me every moment. So thank you so much. And the question is, during your talk, I was thinking about turbulence, and finally you tell me that you're doing it in progress, and all power to you. And the question still is, what about closure of, since you mentioned the tokamak and plasma at the beginning, the closure of Bogolyubov system, that I believe it's still an open question.
I'm not super familiar with that. Like I said, my background is Aero and SciML, and I would think that Josh and Chi, who are the domain scientists in that particular study, would be better suited to answer that question. But I'll make a note, and perhaps we can we can chat about it sometime. But off the top of my head, I would have to say I don't know. Sorry.
Okay, thank you.
Mm-hmm. Other questions? Yeah, I had a quick question for the SDEs. I mean, did you check like the SDEs with the critical transitions, like stochastic van der Pol or these kind of things?
No, we did not. So we, like I said, there's probably a whole bunch of comparisons that can be done on top of this. We looked at some systems that we have access to because of some connections with these geophysical type of applications. So, but yeah, it's possible to extend studies. We should have a manuscript out soon on the archive, and that will have a full list of these types of comparisons.
Okay.
Yeah.
Okay. Thank you. Yeah. Okay. If there are no other questions, we can just thank the speaker again. Thank you very much, Romit.
Yep.
Thank you.
Thank you for the invitation. Thank you everyone for showing up.
Yeah.
Yep.
Okay. Okay. Take care, everyone. Bye-bye. Bye.